Welcome. In this session, we'll dive into problem number 963, minimum area rectangle 2. This is an exciting computational geometry problem that challenges us to find the smallest rectangle that can be formed by points on a 2D plane. Let's explore the strategies and techniques to solve it effectively. In this problem, we are tasked with finding the minimum area of a rectangle that can be formed using a given set of points in a 2D plane. The rectangle can either be axis-aligned, meaning its sides are parallel to the x-axis and y-axis, or it can be oriented at any arbitrary angle. If it is not possible to form a rectangle using the given points, the result should be 0. The input consists of a list of points, where each point is represented as a pair of integers indicating its x and y coordinates. The output should be the minimum area of any rectangle that can be formed using these points, or 0 if no rectangle can be formed. For example, given the points 1, 2, 2, 1, 1, 0, 0, 1, we need to determine the smallest possible area of the rectangle these points can form. The output for the example input 1, 2, 2, 1, 1, 0, 0, 1 is 2.0. In this case, the rectangle with corners at 1, 2, 2, 1, 1, 0, and 0, 1 has the smallest area of 2.0. Notice that this rectangle is not aligned with the x-axis or y-axis but is instead oriented at an angle. Another example is when the input is 0, 1, 2, 1, 1, 1, 1, 0, 2, 0. Here, the output is 1.0 because the rectangle formed by 1, 0, 2, 0, 2, 1, and 1, 1 has an area of 1.0. This rectangle, unlike the previous one, is aligned with the x-axis and y-axis, making it axis-aligned. In another example, if the points are 0, 3, 1, 2, 3, 1, 1, 3, 2, 1, 2, 3, the output is 0. This is because no rectangle can be formed with these points. The key takeaway here is that if it is not possible to identify 4 points that form a rectangle, the result must be 0. Now, let's consider the constraints of the problem. The input list can have anywhere between 1 and 50 points, and each point is represented as a pair of integers. Additionally, the x and y coordinates of the points can range between 0 and 10,000, and all points provided in the input are guaranteed to be unique. There are several edge cases to keep in mind for this problem. First, if there are fewer than 4 points, it is impossible to form a rectangle, so the output should be 0. Second, if all the points are collinear, meaning they lie on the same straight line, no rectangle can be formed, and the result should again be 0. Third, the solution must account for rectangles that are not aligned with the axis, ensuring that rectangles formed at arbitrary angles are considered. Finally, the implementation must handle cases where the x and y coordinates are very large, up to 10,000, without running into performance issues. These considerations are essential for solving the problem robustly across all possible inputs. To tackle the problem of finding the minimum area rectangle that can be formed by a set of points in a 2D plane, we first consider several possible approaches. One straightforward method is the brute force approach. Here, we generate all possible quadrilaterals from the given points and check if each one forms a rectangle. A rectangle is defined by specific geometric properties. Opposite sides must be equal in length, and the diagonals must also be equal in length. These properties can be verified using distance formulas. However, the brute force approach has a major drawback. Generating all combinations of 4 points requires n to the power of 4 computations, where n is the number of points. Since the problem allows up to 50 points, this approach quickly becomes computationally infeasible for larger inputs. This leads us to explore more efficient strategies. One such alternative is the optimized approach using geometry and hashing. Instead of exhaustively generating rectangles, this method focuses on pairs of points that can form diagonals, as diagonals uniquely define the rectangle. By reducing the problem to diagonal properties, we can significantly cut down redundant calculations. In the optimized approach using geometry and hashing, we begin by iterating through all possible pairs of points. For each pair, we calculate the midpoint and the squared length of the diagonal. These values are stored in a hash map, where the key represents the diagonal's midpoint and slope, and the value is a list of point pairs that share this diagonal. This structure enables us to efficiently check for matching diagonals that could form a rectangle. When two diagonals have the same midpoint and slope, they define a rectangle. We can then compute the area of this rectangle and update the minimum area if it's smaller than the current minimum. This approach has a computational complexity of n squared, which is a significant improvement over the n to the power of 4 brute force method. Additionally, it avoids redundant calculations by leveraging geometric properties. Another approach we considered involves rotational geometry, using vector properties and rotation matrices to verify perpendicularity. However, this method introduces higher implementation complexity and is prone to floating point precision errors, making it less practical compared to the hashing strategy. The optimized approach using geometry and hashing was ultimately chosen for its efficiency and clarity. By focusing on diagonals as the defining feature of rectangles, we reduced the problem's complexity from n to the power of 4 to n squared, making it computationally feasible for larger inputs. The key insight here was recognizing that rectangles are uniquely determined by their diagonals, allowing us to utilize hash maps for efficient storage and lookups. This method also avoids the numerical precision issues inherent in rotational geometry and the inefficiency of brute force. One pivotal observation was that by focusing on midpoints and slopes of diagonals, we could streamline the problem and eliminate unnecessary calculations. However, this approach does come with trade-offs. It requires careful handling of hash map keys to avoid collisions and ensures numerical stability by working with squared distances rather than raw floating point values. While the brute force method was too slow and the rotational geometry approach introduced complexity, the geometry and hashing strategy strikes the best balance between performance and simplicity, making it the most practical solution for this problem. To solve the problem of finding the minimum area of a rectangle that can be formed using any 4 points on a 2D plane, we start by understanding the input in the brute force approach. The input is a list of points, represented as tuples of their x and y coordinates, such as x1, y1, x2, y2, and so on. To make our computations efficient, we store these points in a set, allowing for constant time lookups. The first step in the brute force approach is to iterate over all possible pairs of points. These point pairs will act as the diagonally opposite corners of potential rectangles. For each pair, we label them as P1, which is x1, y1, and P2, which is x2, y2. Now, to determine if these points can form a rectangle, we need to ensure that the vectors formed with the other two corners satisfy the orthogonality condition. This brings us to the next key step, checking if the vectors are perpendicular, which we can verify using the dot product. If the dot product is 0, the vectors are perpendicular, and we can proceed to identify the other two corners of the rectangle. Once we have identified a pair of points, the next task is to compute the third and fourth points of the rectangle. Using the perpendicularity condition, we calculate the coordinates of these two missing corners. After computing the coordinates, we check if these points exist in our set of input points. If they do, we know we have a valid rectangle. With a valid rectangle identified, we then calculate its area. The area is the product of the lengths of two adjacent sides. These lengths are computed using the distance formula, which involves the square root of the sum of squared differences in x and y coordinates. For example, the length of one side is determined by the distance between P1 and P2, and the other side is calculated based on the distance between P1 and the third corner. Once the area is computed, we compare it with the minimum area found so far. If the new area is smaller, we update our minimum. Lastly, we need to account for edge cases. For example, if no rectangles can be formed, we need to return 0 or an appropriate message. In scenarios where no rectangle can be formed, either because the input has fewer than 4 points or the points do not allow the formation of a rectangle, our algorithm will handle this by returning 0. To ensure correctness, duplicate points in the input should be removed before starting the calculations. This avoids unnecessary computations and ensures that the algorithm only considers unique points. Additionally, if the input contains fewer than 4 points, we can terminate early since it is impossible to form a rectangle. Finally, the output of the algorithm is the smallest area found among all valid rectangles. If no rectangles are possible, as mentioned, the output will simply be 0. To summarize the key insights, the orthogonality condition plays a critical role in identifying rectangles, as the dot product of two perpendicular vectors equals 0. Efficient lookup is achieved by storing points in a set, allowing us to quickly verify the existence of the computed third and fourth corners. While the brute force approach scales quadratically with the number of points, the use of a set ensures that rectangle validation is fast, keeping the overall complexity manageable. To implement this algorithm effectively, we rely on two primary data structures, a list and a set. The list is used to store all input points, making it easy to iterate through them and generate point pairs. However, for efficient lookups, we convert this list into a set. The set allows us to check the existence of computed points, such as the third and fourth corners of a rectangle, in constant average time. Optimizations can further improve the algorithm. For instance, we avoid redundant computations by leveraging symmetry. Once a pair of points, such as P1 and P2, is processed, we do not reprocess them in reverse order as P2 and P1. Deduplicating the input points at the beginning also prevents unnecessary calculations and ensures the input is clean. Another optimization is early stopping. If at any point, the area of a rectangle is found to be smaller than the current minimum, we can skip further calculations for that pair. These techniques collectively help streamline the algorithm and reduce overhead. Finally, let's analyze the complexity of the algorithm. The time complexity primarily comes from generating all pairs of points, which requires n² operations for n points. For each pair, checking the existence of other points and calculating the area takes constant time, resulting in an overall time complexity of n². In terms of space complexity, storing the input points in a set requires n space. This space is proportional to the number of unique points in the input. While the brute force approach is not the most optimal solution, these complexity bounds demonstrate that the algorithm is feasible for moderately sized inputs. By carefully managing our data structures and applying optimizations, we can handle this problem efficiently within the given constraints. Here, we begin the Python implementation by importing the square root function from the math module. Then, we define the solution class in the min-area-free-rect method, which takes a list of points as input. First, we determine the total number of points and convert the list of points into a set for quick lookup. We also initialize a variable, min_area, to infinity to keep track of the smallest rectangle area found. Next, we use three nested loops to select all possible combinations of 3 points from the input. For each triplet of points, represented as P1, P2, and P3, we calculate the vector differences V1 and V2, which represent the edges of a potential rectangle originating from P1. To check if these vectors are perpendicular, we use the dot product. If the dot product equals 0, the vectors are orthogonal, meaning they could form two sides of a rectangle. Now, we compute the coordinates of the fourth point required to complete the rectangle by adding vector v1 to the coordinates of P3. This gives us the potential position of the fourth corner of the rectangle. If the calculated fourth point exists in the set of input points, we proceed to compute the area of the rectangle. The area is calculated as the product of the magnitudes of vector v1 and vector v2, which are the lengths of the rectangle's sides. To find the magnitudes, we use the square root of the sum of the squares of the vector components. After calculating the area, we update min_area with the smaller value between the current min_area and the newly computed area. Finally, after all iterations are complete, we return the minimum area found. If no valid rectangle was identified, we return 0 as the output, ensuring the function handles cases where no rectangles can be formed. Here, we begin by importing the necessary libraries and defining our class and method. The function min_area_free_rect takes a two-dimensional array of points as input. Our first step is to initialize the number of points, n, and create a hash set called pointSet to store each point as a string in the format x, y. This will help us quickly check for the existence of points later. We then declare a variable min_area and set it to double.max_value, which serves as our placeholder for the smallest rectangle area we find. Next, we use three nested loops to iterate over all combinations of 3 points. For each triplet of points, P1, P2, and P3, we calculate vector differences. Specifically, V1 represents the vector from P1 to P2, while V2 captures the vector from P1 to P3. These vectors allow us to determine the orientation of the points. To check if these vectors are orthogonal, we calculate their dot product. If the dot product equals 0, it means the vectors form a right angle, which is a necessary condition for a rectangle. When this condition is met, we proceed to compute the coordinates of the fourth point, x4 and y4, by extending vector v1 from P3. Now, with the coordinates of the fourth point x4 and y4, we check if this point exists in point set. This ensures that the 4 points form a valid rectangle. If the point is present, we calculate the area of the rectangle. The area is determined by multiplying the lengths of the two orthogonal vectors v1 and v2, which we compute using the Pythagorean theorem. Once we have the area, we compare it with the current min area and update min area if the current area is smaller. Finally, after all iterations, we check if min area remains unchanged. If it is still max_value, it means no rectangle was found, so we return 0. Otherwise, we return the smallest rectangle area stored in min area. This approach ensures that we efficiently find the minimum possible area of any rectangle formed by the input points. To solve this problem, we start by storing the input points in a set. This allows for quick lookup operations, which will be essential as we verify potential rectangles. We also initialize a variable min_area to infinity, which will track the smallest rectangle area we find during the process. Next, we iterate over all unique combinations of 3 points from the input. For instance, consider the triplet 1, 1, 1, 3, and 3, 1. From these points, we calculate two vectors, v1 from 1, 1 to 1, 3, which is 0, 2, and v2 from 1, 1 to 3, 1, which is 2, 0. We then check if these vectors are orthogonal by calculating their dot product. If the dot product is 0, the vectors are perpendicular, which is a key property for forming a rectangle. Here, the dot product is indeed 0, so we proceed to find the fourth point of the rectangle, calculated as x4, y4 equals 3, 3. We confirm that this point exists in our point_set. Once all points are validated, we calculate the area of the rectangle using the magnitudes of the vectors. The area in this case is 4, and since it is smaller than our current min_area, we update min_area to 4. For other triplets of points from the input, we repeat the same process, verifying orthogonality, computing the fourth point, and checking its existence in the set. However, in this specific example, none of the other triplets yield a smaller rectangle than the one already found, so the minimum area remains 4. Now, moving to a new input scenario, we consider a less structured set of points 0, 0, 1, 2, 3, 1, 1, 0. As before, we initialize our point_set and set min_area to infinity. We then start iterating over triplets. For the first triplet 0, 0, 1, 2, and 1, 0, we calculate the vectors v1 and v2 as 1, 2, and 1, 0, respectively. Next, we check the dot product to determine if these vectors are perpendicular. The result is 1, which means they are not orthogonal. Since orthogonality is a requirement for forming a rectangle, we skip further calculations for this triplet and move on to the next. In this second example, we eventually find a valid rectangle configuration with the triplet 0, 0, 1, 2, and 3, 1. The vectors v1 and v2 are computed, and their dot product confirms they are orthogonal. However, when we calculate the coordinates of the fourth point needed to complete the rectangle, we find that it does not exist in the point_set. This means no rectangle can be formed with this triplet, and we continue checking other combinations. Ultimately, for this set of points, no rectangles are found, and the output is 0. Now let's analyze a more complex input where the points form a shape that includes a rectangle 0, 0, 2, 0, 0, 2, 2, 2, 1, 1. We initialize our point_set and min_area as before and begin iterating over triplets. For the triplet 0, 0, 2, 0, and 0, 2, we calculate the vectors v1 equals 2, 0, and v2 equals 0, 2. The orthogonality check passes because the dot product is 0. Using these vectors, we compute the fourth point 2, 2, and find it exists in the set. With all points verified, the area calculation gives 4, which updates our min_area. As a result, the output for this input is 4, representing the smallest rectangle area formed from these points. Now, let's break down the time complexity of the algorithm step by step. The most significant factor comes from the 3 nested loops that iterate over all unique triplets of points. If we have n points, the number of ways to choose 3 points is given by the combination formula n3, which simplifies to n*, n1*, n2/6. This results in a time complexity of n³ for the outer loops. Within each triplet, there are several operations performed: calculating vector differences, checking orthogonality using a dot product, computing the 4th point, verifying if that 4th point exists in the set, and finally calculating the area. Each of these operations is constant time, or O1. Since all operations inside the inner block are O1, and there are n³ triplets, the overall time complexity of the algorithm is n³. This efficiency stems from the fact that we've limited the computationally intensive part to the triplet selection and avoided unnecessary iterations over all point combinations. Next, let's turn to the space complexity. First, we account for the input storage. The array of points itself requires n space. Additionally, we use a set, point_set, to store all points for quick lookups, which also contributes n space. Beyond that, the algorithm employs a few auxiliary variables like min_area, v1, and v2 for intermediate calculations. These variables are constant in size and do not depend on the number of input points, so they contribute O1 space. When we combine these factors, the overall space complexity is determined to be n, which is efficient given that we are only storing the essential data needed to perform the computations effectively. To put this into context, let's compare the current approach with a brute force method. A naive solution would involve iterating over all possible quadrilaterals formed by 4 points and checking if they satisfy the conditions of a rectangle. Since there are n⁴ such combinations and verifying each rectangle takes O1 time, the brute force solution has a time complexity of n⁴. In contrast, the optimized approach reduces this to n³ by focusing on triplets and leveraging vector mathematics to determine rectangles efficiently. This improvement is achieved by checking orthogonality and using a set for constant time point lookups, which eliminates the need to consider all 4-point combinations. In terms of best, average, and worst-case scenarios, the algorithm consistently processes n³ triplets, regardless of the distribution of points. While the best case may involve fewer points overall, the big O complexity remains n³ in all cases. Finally, let's solidify this understanding with a mathematical proof. The dominant factor in the time complexity arises from the triple nested loops, which iterate over n3 triplets. Since n3 is proportional to n³, and each triplet operation involves O1 computations, the total time complexity is conclusively n³. On the other hand, the space complexity is straightforward to calculate. The input points and the set for lookups both require n space, while the auxiliary variables used during calculations are constant and do not depend on the size of the input. This leads to an overall space complexity of n. In conclusion, the algorithm strikes a balance between time and space efficiency, significantly improving upon the naive n⁴ approach by reducing the time complexity to n³, while keeping the space usage minimal at n. When tackling this problem, there are several common pitfalls to watch out for. First, it's important not to assume that the rectangle must be axis-aligned. This is a common oversimplification that leads to missing cases where the rectangle might be rotated. Another issue arises when duplicate points in the input are ignored. If duplicates aren't handled properly, they can lead to incorrect area calculations or even runtime errors. Then, there's the temptation to use a brute force approach, checking all possible combinations of points. While this might seem straightforward, it's computationally expensive with a time complexity of n⁴, making it unsuitable for larger datasets. Additionally, precision issues can occur when working with floating point arithmetic, particularly for non-axis aligned rectangles where calculations might involve trigonometric functions or cross products. These precision errors can result in incorrect outputs or comparisons. Finally, it's critical to verify that the 4 selected points actually form a valid rectangle. Not all combinations of 4 points meet this condition, and skipping this validation step can lead to invalid results. Now, let's focus on some insights that can help you during interviews. For axis-aligned rectangles, a key optimization involves hashing the diagonal points or using a set to store scene pairs. This can reduce the complexity to n squared. For the more general case of rotated rectangles, geometric properties like slopes and angles between points become essential. Recognizing patterns is also vital. Many geometry problems, including this one, benefit from leveraging concepts like symmetry, hash maps, vector properties, or slope calculations. It's important to articulate your thought process during the interview to demonstrate how you arrive at these insights. Another critical aspect is optimization. You should emphasize reducing redundant computations, such as by pre-computing distances or slopes between points instead of recalculating them multiple times. Don't forget to address edge cases, situations like all points being collinear, the presence of duplicate points, or cases where there are fewer than 4 points in the input. Related problems, such as detect squares, max points on a line, or minimum area rectangle, provide excellent practice and share similar concepts that can reinforce your understanding. Let's explore alternative approaches and the trade-offs involved. A brute force method, which involves checking all combinations of 4 points, is straightforward to implement but highly inefficient with a complexity of n to the power of 4. It quickly becomes impractical for larger datasets. For axis-aligned rectangles, an optimized approach uses hash maps to store scene points, reducing the time complexity to n squared. While efficient, this method is limited to the restricted case of axis-aligned rectangles. For the general case of rotated rectangles, geometric techniques come into play. Using vector cross products or trigonometric calculations allows for computing areas of rotated rectangles. However, this introduces challenges with numerical precision and can make the implementation more complex. Another alternative is the convex hull approach, which reduces the search space by focusing only on the outer boundary of the points. This is particularly useful for finding a minimally bounding rectangle, but it might not apply to cases where the rectangle lies within the set of points. Each approach comes with its own trade-offs, and the best choice often depends on the problem's specific constraints and requirements. Great job! We've summarized the key insights from problem number 963, minimum area rectangle 2. Remember, mastering these types of problems strengthens your geometry and algorithmic thinking. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!